So I'm here to talk about functional languages for functional GPU programming. So this is a bit of work I did as part of my undergraduate project in York. And so why GPUs? As we had some talks yesterday about GPUs and parallelism. And so GPUs are very powerful processors, and they're parallel, and it's important for us to harness their power. And we found them everywhere now. But they're a bit difficult to program because they have a different architecture, and the languages such as CUDA that we have nowadays are very low level. So thankfully, we have functional languages. We're ICFP after all. And we have some mechanisms such as higher order functions, algebraic data types, and type classes that can help us raise the level of abstraction. The aims of my project were three. So first, I wanted to compare these two languages, see what features they offer, and come up with a nice summary, which I'll show you in a bit, to help developers get more information about which language to use. Second, I wanted to compare the performance of Obsidian and Accelerate against hand-coded CUDA. And finally, try to see if these languages are ready to be used as normal GPU languages. And so, what Accelerate and Obsidian are? They are domain-specific languages. They are embedded in Haskell, and even though they attack the same problem, so they generate CUDA code automatically, they follow very different philosophies. So some of you already know what Accelerate and Obsidian are, but for the ones who don't, Accelerate is a stratified language. It has a front end where we specify our computations and a back end that interprets the code for different architectures. In this case, I only looked at the CUDA backend. This is based on the instantiation of algorithmic skeletons. And one feature or one characteristic of Accelerate is that it completely hides the GPU details. So everything happens implicitly, and the programmer doesn't have any control of what's happening inside the GPU. And as you can see in the diagram, it is capable of online compilation, so we can just run our GPU programs without never leaving Haskell. Obsidian is a bit different. It also solves some of the abstraction issues, so we program in a Haskell-like language, but we remain in control of what's happening inside the GPU. Similarly, we can do online compilation, but we can also generate standalone kernels. So we can use this language to produce a CUDA source file that we can then use in other CUDA projects. And so one of the results of the work I did here was to get all the features of these languages and compare and see what they offer. So we already talked about compilation and the manipulation of CUDA internals. In terms of expressiveness, well, they owe most of their characteristics to Haskell. We can see that, for example, Obsidian, the developers say that it's capable of some level of nested parallelism, while Accelerate, that's strictly forbidden. And the API, so Accelerate provides a nice library of functions that we can use and are ready to use and well documented, while Obsidian is still not there. So that might influence the decision of some developers. In terms of safety, well, we have type safety because of Haskell. Accelerate provides some debugging options that are good when dealing with the GPU programs, but sadly none of them can catch CUDA errors. So once we are running our CUDA programs, if we have a runtime error, we cannot see that directly reflected in our Haskell program. So just a small example here. This is how we do, say, dot product in Haskell. Accelerate is very similar. We just have one run function that tells us that this would be running on the GPU, or for that matter, any other backend that Accelerate provides. Obsidian is a bit different, and important here is to know that this function, execthread, is the one telling that we are going to run this function at the thread level of the GPU. It's important to compare this to something like we would do normally in Haskell. This is the same program, so dot product just using shared memory. And we need to take care of everything that happens inside the GPU. So this is, as you can see, very error prone. So Accelerate and Obsidian already solve some of the abstraction issues we might face. So we compare performance. This is parallel reduced. So what we did here is just take an array of integers and sum them together in parallel on the GPU. And we find that the CUDA version, which only uses shared memory, so there are no big optimizations in this program, is faster than what Accelerate and Obsidian produce. This was somewhat surprising because Accelerate has an algorithmic skeleton, so a piece of code that gets instantiated that correctly matches this program. And another thing is that the CUDA version and the Obsidian version do the last pass of the reduction sequentially on the CPU. Then we also compared matrix multiplication, and we compared, so we used a very naive implementation in Accelerate, also in Obsidian, and we tried to improve the Obsidian version by forcing more rows of the matrix into the shared memory. And we use a CUDA version that uses some optimization in the use of the shared memory. We can see that better in the graph. And again, CUDA is the fastest one. The optimizations we did in Obsidian were not that useful, and we hit a bug in Accelerate after using matrices with more than 16 million elements. And we talked to some of the Accelerate guys, and this bug is, I think, still there on the repo, and I don't know if maybe they're not solved, or maybe we need to double check or change the algorithm I was using. So in conclusion, in my experience, I have to say that Accelerate and Obsidian solve the abstraction issue to a great extent, so it's way more easy and amenable to program in Accelerate and Obsidian than it is in CUDA, say. But they're still behind hand-coded CUDA. Thankfully, they are still under active development, so maybe this gap in performance is already reduced, because I ran these benchmarks back in April, I believe. And some recommendations, so I would stick to CUDA. Is speed is your main concern in your project. Maybe using Accelerate for existing Haskell programs where you only want to optimize small bits of your program. And if you just are getting started and want some control over the GPU, then probably Obsidian is the language of choice. Thank you.
I have a question. Is any of these frameworks allow you to combine Haskell generated CUDA code with handwritten CUDA code, kind of like inline CUDA assembly?
So I know that with Obsidian, for example, you can generate your CUDA files. So you can generate some CUDA kernels and dump that to a file that then you can plug into some CUDA programs. But I'm not sure if you can interchangeably mix the languages.
There was an interesting talk on GPU programming yesterday, I think, about how far you can go with specific optimizations.
Yeah.
The CUDA code that you compared is not optimized in this way, if I understood what you said.
Yeah, no.
And my question is, can you perform the optimizations with Accelerate and Obsidian? I would guess from what you said that with Obsidian it should be possible.
Yeah, I believe Accelerate, what they do is, so they have this similar to the talk yesterday. They are based on algorithmic skeletons. They don't do any like searching in the space for optimal solutions, but they do query your machine to get GPU information and try to lay out all the computations better in the GPU. In Obsidian, it's more or less down to how you program. So we are advised to follow CUDA best practices, so using shared memory and managing adjacent threads and stuff, but you're pretty much on your own. I mean, you can write optimal programs, but you need to take care of how you do that.
Thank you.
So here your recommendation is basically about what one should use now given the existing tools. Do you have any more constructive suggestions about what one wants to build better?
Well, I guess the main concern, I mean, we're talking about GPU, so speed is probably your main concern. I did some work a few years ago, and all the work done with GPUs was we want just speed. So, and this can be really tricky because you need to manage all these threads and memory and stuff. So I think these languages, I mean, they're going the right way. So we are already going and solving some of the abstraction problems, but there may be some ways to improve that, to just bridge or reduce the gap in performance, which that's the main concern. But I believe, if development, I've talked to, I think some of the people that develop Accelerate and Obsidian are here, and they're still working on it. So I guess that's probably that the gap has been reduced already.